Okay. So, real quick, let's run through the agenda, even though you guys can see it. So, we just did our little icebreaker game. I hope you guys had fun with it. I have fun looking at all your answers. So now we have a couple minutes where you guys can ask me, excuse me, where you guys can ask me any questions you have, either on the past content, past material, any questions that we've done before, anything like exam related, final related. I don't know why all of the sounds are happening. Is there a list of what to know for this chapter? I'm so glad you asked. Yes, there is. So there's one that Dr. West made, which I believe is either already on Canvas or it will be on Canvas soon. I also have that what to study guide thing that I made you guys. I'm working on the chapter 18 stuff. It doesn't look like there's much more to add. So I'm probably going to finish that up tonight and send it to you guys tomorrow morning. And then Dr. West will also send you guys like a final exam list of topics. And so hopefully that'll be super detailed as well. That was a mouthful. I don't know why I say so much for simple questions. Anything else? Also, I did look on the syllabus, and it is like 64 questions, I believe, is what it says, and it's like 120 minutes, something like that. So you guys are right. That's what it says on the syllabus. Hopefully that's still true and he doesn't change anything, but I will wait to hear back from him directly, and then I'll pass that information to you guys as well. And then the question was, do you know when he will release that study guide for the final? I'm honestly not sure. I hope he does it sooner than later. Wait, by study guide, do you mean like the practice final or the like list of topics for the final? The practice final. Okay. Usually you guys have Monday, Wednesday, Friday class, and then the Tuesday, Thursday class. So if the final exam is like Thursday, I believe he'll give it to you 2 Thursdays before. Or if the final for you is on Friday, he'll give it to you 2 Fridays before. That's how he usually does it, at least. And then when is your final? I don't remember exactly when it was. I believe it's December 12th or 13th, depending on which class you're in. But someone fact check me, please. And then, usually, I forgot to mention this, usually he does the practice final, like, on a Scantron, and then you have to turn in the Scantron, but clearly, since you guys are online, you can't do that. I believe it's going to be one of those WebEx assignments, like a quiz or exam. I don't know exactly how he's going to do it, but that'll be the format that you guys should prepare for. So is that practice final similar to the actual final? Yes and no. So depending on the practice final that he gives you, it can either be a lot easier or a lot harder than the final. And what I mean by that is, okay, that was probably not the best way to go about saying that. But essentially what he does is he sends you either a practice final that was a final for a previous semester, or like a huge list of compiled questions from his practice problems. So it's similar to the final, but it's not going to be exactly that way, especially because it could change like what chapters he chooses to focus on this semester, things like that. So it's pretty similar, but if it's like a practice final that looks really difficult and you're like, oh my gosh, I don't know what to do, or it's like, oh, this is way too easy, it's probably going to be somewhere in the middle. It's not going to be super easy or super, super hard, in my opinion. And then someone said, will he repeat previous exam questions? So in my experience, he might repeat a couple questions. but usually they're going to be like similar questions, just not exactly the same. So they'll look pretty similar, but it might be like a slightly different molecule or a slightly different number, things like that. But he does repeat at least like one or two usually. Will you guys have the whole 2.5 hours? When he's in person, Dr. West usually caps it at an hour and a half, and he gives you guys less questions. Since you guys are online, though, I think you do get the entire 2 hours. And then someone said, would it help to study previous exams if we can review them with Dr. West? Yes, for sure. A lot of the final is going to be material that you've already covered. So if you go back and you can review your exam, definitely do it, because then you're able to see like what kind of questions did you get wrong, what was your issue. Like I know for me, I didn't do like too hot on the chapter 11 and 12 exam when I took the class, so I went back and I reviewed it and I realized what my mistakes were, and so I did really well on that on the final. So if possible, for sure review your exam. How many questions is the final? I believe it was 64, somewhere in that range. And then someone said you can see the exam review videos he posted on Canvas. I didn't know that's how he chose to do that. That's interesting. But yeah. See, I'm not the, someone asked, is it all of the questions? That's what I'm not sure about, because I haven't actually watched those. I haven't had time. I know he said there's going to be a huge bank of questions for the exam, so I don't know if he went through and used all of them. So it's worth emailing him and seeing what you can do, but if he doesn't get back to you, watching those videos is probably the best way to go. And so I said, is there a way to know which ones you got wrong? Again, email him. There is... Hold on. Where's Canvas? So if you guys go to the class, or go to, you go under modules, it says exam review procedure. So, oh, just kidding. I meant review videos for exam. So there's that. And then there's also the post-exam reviews. So you can go here. And this is what I'm guessing is him just reviewing all the questions from the exam. You can see the average and all that kind of stuff. So this is the best way to go, I think. You can for sure try to email him just to see your exact test and what you got wrong. But as some people are saying in the chat, he sometimes doesn't answer. So yeah, that's the best I can advise you guys, if that makes sense. Oh, also, you guys have a TA now. So you can also email the TA. I believe TAs are able to review your exam with you. So if Dr. West doesn't respond, for sure, email the TA. So... all right, so we should be good with the agenda. I'll open up Notability so we can get started. And yeah, I know it's really hard with Dr. West. Someone said I don't even know what Dr. West looks like. He's just so busy, and he's like, I think he's very introverted. He doesn't really, he likes people, but he's kind of like quiet, doesn't really like that stuff. He's always running around doing research, so I understand, but also I totally understand how frustrating it can be for you guys. But if you want to know, he's a tiny little adorable not Australian, the other one. I can't even remember the name. But whatever. He's a New Zealander, yes. He's a cute little New Zealand man. If you say he's Australian, he gets very upset. All right. So, let's get to the practice problems. If you guys have any more questions, let me know. We can talk some more again at the end, but I do want to get through a couple of these practice problems at least. And thank you for the nice comments in the chat. You guys are too sweet. Okay, so we are going to do these the rosemary way, and then we can go through and do a couple of them the long way as well, just so you guys can see the reaction mechanism again. So, what is the first step of the rosemary method? What do we do? Yes, identify and cross out the leaving group. So, here we have an anhydride. So we have two carbonyls, so it might be kind of hard for you guys to see like which one is the leaving group. So I want to point out, just remember that leaving groups can be anything that is like a heteroatom bonded to a carbon. We're never going to break carbon-carbon bonds. We're never going to break carbon-hydrogen bonds. All we're going to do is break carbon bonds to heteroatoms. So in this case, I have highlighted those two options for us. And also in this case, this anhydride is symmetrical, so it doesn't matter which side you cut off as the leaving group. I just like to have consistency, so I always cut out the right side. So we're going to say this whole thing is the leaving group. Next, we have our nucleophile. So as you guys said, what is our nucleophile here? And I want you to be as specific as possible. Perfect answer, you guys. The nitrogen. Exactly. So that is our nucleophile. Cool. And what is the last thing we have to remember to do? It has to... Yes, awesome. Remove one of the hydrogens. So I'm going to cross out this 2. Perfect. So we're going to leave this part the way it was. We got rid of the leaving group. And now we're going to attach our nitrogen. Remember, the reason we're super, super specific about that nitrogen being the nucleophile is because that is what will attach to this carbonyl. And then attached to the nitrogen, we have this carbon chain. And we have one hydrogen left over. Please remind me what functional group this guy is, please. He's an amine. Yeah, sorry. He's an amine. Sweet. So, nope, not an amine. Amide. That's my bad. I got too excited. He's an amide. All right, so we know it's an amide, and now I want you guys to answer one last question for this. It's a concept question. Was this reaction favorable? And what I mean by that is like stability-wise. Was this favorable? Yes, yes, yes. Cool. Everyone's saying less. Everyone is saying yes. And then someone said that's because the most stable group you can make is the amide. And so we did go from more to less reactive. Perfect. You guys got perfect answers. So this was favorable because we went from more to less reactive. Yay! Any questions on this one? If not, let's go down to the second one. Everyone automatically looks at this and they're like, what is that? I don't want to go anywhere near it. And I totally understand why, because we have 2 carbonyls. And now, instead of an anhydride-looking thing, we actually have 2 separate carbonyls, right? This is weird. But let's just stick to the rosemary method. Stay calm. Don't freak out. First things first, what is going to be our leaving group? Yes, awesome. So someone said the ester. And then someone also specified that it's the carbon-oxygen bond. Perfect. So this guy is going to break right here. So this is the leaving group. And then what is going to be our nucleophile? Oh, my bad. I saw people saying "oh" in the chat, and I thought it was like "oh," and I was like, what happened? Yes, it would be the O from the OH group. So that's going to be our nucleophile. And what's the last thing we're going to do? Remove the hydrogen. Awesome. So we're going to go ahead and add our oxygen, which would make this into an anhydride. Ta-da! And someone in a previous semester also pointed out to me that you could also use this one as the nucleophile and this one as the electrophile. You can definitely do that. Like I said, there's a couple different ways that you can go about doing reactions, but this was the main one that I wanted you guys to think about. But what if... I don't know what I was trying to say. Reset. So what is the name of our product? What is the functional group name? Anhydride. And is this still an acetic anhydride? Can we still call it that? No, perfect, good. Glad we got that. So we went from an ester to an anhydride. Was that a favorable transformation? No, why not? Yes, because we went from less to more reactive. So this would happen because I'm telling you it happens, but it's not going to be favorable. So it's possible to make this happen, but it's not favorable because we went from less reactive to more reactive. So essentially we made it go from more stable to less stable. And then someone asked a great question, which was, why would that not be considered acetic anhydride? And I'm glad somebody asked because I knew people were thinking it. So acetic anhydride is going to specifically be this guy right here. And the reason it's called acetic is because this is like the acetal functional group when it has one CH3. So we call that acetic anhydride. Any other R group is still going to be an anhydride, but it won't have the acetic in front of it. It'll have a different name. Make sense? I know I just said a lot at once. Okay, any questions about this reaction that we just did? Alrighty. So the last thing I want to say about it is... Actually, no. That's fine. Sorry, I keep wanting to say stuff and then I'm like, they don't need to know that. Alrighty, so you guys know the drill. What's the leaving group? Where am I going to chop off? What bond? Awesome, so the carbon-sulfur bond. Exactly. So this whole thing will be the leaving group. And what's going to be our nucleophile? The nitrogen. Cool. So that's our nucleophile. That's our leaving group. So I don't know why I thought this was like going to make it like spicy and fun, but I put the leaving group on the opposite side. So remember to like orient yourself. Don't get confused by that. We're going to add the nitrogen here. Remember, we get rid of that last nitrogen. And we get bam, bam. And we know that this is called what? Amide. Sweet. Last thing. Is this a favorable reaction? Yes, because we went from more to less reactive. Awesome. So for this last one, you guys already know the drill. What is our leaving group? The OH, exactly. This is the bond we're going to break. Perfect. What's our nucleophile? Sulfur. Okay, what's the last thing we got to do? Drop the hydrogen. Perfect. All right. Ta-da! And now please tell me what this guy would be called. The thioester. Perfect. Okay. So I just want to, I'll send an email about this as well, but I just wanted to clarify something that I said because I had made a mistake on Wednesday or whenever we went over this. So I looked it up in Dr. West's PowerPoint, and thioesters are less reactive than carboxylic acids and esters. That was completely my bad. I apologize. If I confused you guys, I apologize. So the actual order goes like so. I'm sorry you can hear my dad in the background. Wait, I gave it to you like this? Oh. There's nothing going on up here, guys. I'm so tired. Then just I take back my apology. No, but seriously, I think I might have done it wrong in tutoring then. I know I said it backwards in one session. So whoever I said that to, I apologize. I will send an email just clarifying that this is the correct way to do it. So cool. So now that we have that down, was this a favorable reaction? Yes, because we went from more to less reactive. Perfect. So I will also just do this so you guys know it's separate. I will zoom out so you guys can take a look at all of these at once. Do we have any questions on the reactions we did on this page? I'll give it a couple more seconds before we move on because I know it's like hard to type sometimes. So I have an extra page, as you guys can see, just because I'm going to draw a couple of these, so we have more space to do it. But before we do these examples, I want to actually cover one thing because I don't have a good example coming up. So when we started this chapter, I said there were only going to be two names that you really have to know, like specific reaction names. So we're going to cover that right now. in general, what is the name of all these reactions in chapter 17? Nucleophilic acyl substitutions. Awesome. So they're all nucleophilic acyl substitutions. And so the specific one you have to know is a Fischer esterification. And as you can tell from the word esterification, we are going to make an ester. So we can start with anyone really, but let's just say carboxylic acid. And what are we going to want as our reagent in order to turn this into an ester? What do y'all think? Well, this is true. Yes, we definitely need acid or base, and we can use either. So I'm going to say acid or base catalyst. For sure, that's correct. Someone said alcohol. Yes, a couple people said alcohols. Perfect. So we need some kind of alcohol in order to turn this into an ester. So in the end, we will get this. And again, we can fill any R group in here. So a Fischer esterification is any time we react any other carboxylic acid derivative besides an ester with an alcohol and acid or base, and we create an ester. A specific type of esterification is something called a trans esterification. And this is just when we go from one ester to a different ester. I could do this in terms of R groups, but I'll show you guys an actual R group just to kind of make this easier. So we start out with an ester, and we have to have an alcohol with a different R group as our reagent. So let's say we have something like that, right? Oh. And again, we can have any acid or base. And we're going to end up with an ester that is different than the one we originally had. Why am I like this? Okay, there we go. So in general, Fischer esterifications are creating an ester. Specifically, a trans esterification is when we go from one ester to another ester with a different R group. And these can be done in acid or base catalyst. Any questions? So we've seen reactions like this before. Nothing different is going to happen. This is just one of the ones that he can ask you like the name of. So just know if you make an ester, it's going to be an esterification. Alrighty, if we don't have any questions, we'll do the next one. So the second reaction that he could ask you about is the saponification. And I'm sorry if I spelled that wrong. I tried my best. So a saponification is going to pretty much be like the reverse of the Fischer esterification that we drew in the first example. So let's say we have an ester and we react it with, what do you guys think we are going to react an ester with in order to make a carboxylic acid? And then while you guys tell me that, someone asked, are those the two types of Fischer? I'm sure there's more types of esterifications. But yeah, so Fischer is the big picture, and then a specific type of that is the trans esterification. Come on, guys, give me a guess. What do you think you would have to react with an ester in order to make that into a carboxylic acid? Oh, so saponification? No. Saponification is different. So those are the two different reactions, and then trans esterification is just like a specific type of Fischer. So yes, someone said it. We are essentially going to react with Na or any other positive OH. So once we have NaOH, we will also have a catalyst. I believe this can happen in acid or base, but usually we use H3O plus or H2O. And we are going to end up with a carboxylic acid. Here, let me zoom out so you can see it all at once. So for the mechanism, these are going to be the same mechanisms that we've been doing this whole time. Like all of these examples are going to be pretty much the same. So you kind of have to know the mechanisms in terms of like do them a couple times, practice them, understand the concepts, but you don't have to like draw out mechanisms on the exam. So yeah, the other question was for these, will he just ask the name or the mechanism, things like that. So the reason I give you the name is because, so these are going to be asked exactly the same way as these guys. So these all have the same exact mechanism. They're pretty much all going to be the same concepts, all that stuff. Sometimes he will ask you questions that say like, if you take this ester, and he draws an ester, and you undergo saponification, what will the answer be, right? Or he gives you some other molecule, and he says, if this undergoes a Fischer esterification, what molecule will you make, right? So instead of giving you reagents, he'll just say esterification or saponification. So you just have to know that saponification makes a carboxylic acid, esterification makes an ester. Make sense? And then someone said, isn't this hydrolysis too? So yes, pretty much there's a lot of different reactions that can be considered a hydrolysis. But that is another name for saponification as well. So we can call it either the saponification of an ester or the hydrolysis of an ester. Both are equally correct. He just tends to use saponification. I don't know if that answered your question, but I hope it did. So these were all super awesome questions. Do you guys have any more about this stuff, or can we move on to some more practice problems? I would like to do a couple more, and then we'll do a quick Chapter 17 recap, and then we can call it a day. Let's scroll. All right, so let's do my favorite ones from this page. Okay, so for some reason, every time we put a benzene as a substituent, students tend to freak out. I don't know what it is. Maybe benzene rings are just scary. So that's why I put lots of benzenes to practice. First thing is first. What kind of functional group is this? This guy. What do we think? What kind of functional group? Anhydride. Perfect. Cool. So what is going to be our leaving group? Ooh, now it's kind of tricky because it's asymmetrical, right? So we can either break this bond or we can break this bond. So either sides can be, or either side can be the leaving group. So the secret here is that we can actually have two different products, right? So in the first one, let's do this in blue, and let's cut off this side as our leaving group. This will be our nucleophile, and we get rid of the hydrogen. So one of our answers can be, bam, or, as you guys were saying, we could switch this around and cut off this guy as our leaving group. And so if we did that, we would get this guy. For the purposes of this class, you just need to know that both of those are possible and that you will also make the byproducts, which will be, in this case, that, and in this case, that. But we don't really care about the minor products as much, so this can be our answer, or this can be our answer. Makes sense? And here, let me just, right here, in case anyone wants to take a screenshot, can use either side as a leaving group. Someone asked, so on an exam, it would be both options. So yes, he can either give you both answers, and the answer would be, sorry. Either he could give you both of these as options, and the answer would be like both of these, like both of the above or something. Or he can give you only one of them as a choice, and that would be correct. He would not give you both of these and have you pick one of the two. And then someone asked, would they both be produced at the same rate? That's a great question. Unfortunately, I don't know the answer. Well, okay, they wouldn't both be produced at the same rate just because they're different. The energies would be different. But I honestly am not sure which one would be made more quickly versus which one would have a slower rate. But that's a really great question. Okay, and someone said they were kind of confused about where the nucleophile was being added. So let's do it this way instead.
if we have this guy and we react it with, I don't even remember what I gave you guys. Okay, just an alcohol. We could either cut off this bond, and if we did that, this whole side would be a leaving group. This would be the nucleophile, and then this would go away, right? So in that case, we would get this answer. Alternatively, this could be the bond we're breaking. This whole thing can be our leaving group. That would still be our nucleophile. We still get rid of the hydrogen. So our answer would be that one. Did this way of drawing it out make a little bit more sense than how I had it before? Okay, awesome, cool. So I'll leave this up for a couple more seconds. Alrighty. Okay, so we're gonna do a quick chapter 17 review to end the session, and then I actually really like these questions because these are about lactones. So we're gonna actually, I'll write myself a note. We're gonna quickly finish these ones up on Monday, and then we'll start chapter 18. Sound good with you guys? Chapter 18 is not too bad. It's not too long. I don't remember how long the handout is, but it's not too bad. There's only like 3 reactions, 4, but they're super straightforward. I know I say 3 reactions like they're nothing, but you guys are like, there's 3 more. I totally get it. They're not too bad. We can definitely cover that in less than a week. So, starting out with reactivity, we know that the trend is acetic acid halides. Acid halides are the most reactive. Amides are the least reactive. And so the general trend is we want to go from more to less reactive. That is preferable for us. And we know that we cannot make acid halides via nucleophilic acyl substitution. What do we have to use instead? Do you guys remember? Yes, so we have to start with a carboxylic acid. We have to react that carboxylic acid with PBr3 or PCl3, and then we create the acid halide. Awesome. And then a quick recap of naming esters. Remember that the parent chain is going to come at the end. The chain on the oxygen comes first. So we name starting with the oxygen group, and then we add the group on the carbonyl, and then we add O8. That is our suffix for esters. We also know that if we have something like this, where we know the common name is isopropyl or whatever it may be, also know the long way to write it out. Like in this case, it's 1-methyl-ethyl-butanoate, butanoate, just because sometimes he will try to trick you with that.
And then we know that the reaction mechanism for nucleophilic acyl substitution can be long and complicated. We know that we have to start with either an acid or a base. If we have an acid, we start by protonating the carbonyl, we activate it, the nucleophile attacks. Usually we end up doing a intramolecular proton transfer to make a better leaving group. We kick off the leaving group and we create our final product. We could also learn how to do this the short way, which is essentially the nucleophile attacks, reform the double bond, kick off the leaving group, and we swap the we swap the leaving group for the nucleophile. So I want you guys to practice it this way a couple times, but then essentially for the exam, I want you guys to be able to just look at this and swap the leaving group for the nucleophile. Last concept we did was lactones and lactams. So we know that naming them is super easy. All we really have to keep in mind is making and breaking lactones and lactams, which, like I said, we'll cover a little bit more on Monday. The last thing I want you guys to know about lactones and lactams is how to read a condensed formula and simplify it this way. So the long way to answer this question would be to draw it out and notice that we start from the oxygen, we attack here, we make a 5-membered ring. But I want you guys to eventually be able to just look at this, count 1, 2, 3, 4, and know that that will be a 4-membered ring. Okay, so I know that was kind of a lot. You guys have any last questions, comments, or concerns for Chapter 17? If not, I shall stop the recording. I'll stay on